Okay, let's take a look at this problem. Barium sulfate. Okay, so barium, this problem gave you the KSP of barium sulfate. Oh no. Okay, let's write out the equation first. You have barium sulfate, solid, in the equilibrium with barium ion, and then the sulfate ion. You notice that the ratio is 1 to 1 to 1, okay? So write the KSP. The chemical equilibrium expression is going to be equal to barium cation multiplied by the sulfate ion, okay? So now let's say if the solubility of barium is X over here, sulfate is going to be X also, right? Because ratio is 1 to 1. The KSP value is given 1.1 times 10 to the negative 10, which is going to be equal to X, represents barium, and X represents sulfate. Now, if you solve for X, okay, X will be X will be equal to square root 1.1 times 10 to the negative 10. You take out the root, it's going to be 1.0 times 10 to negative 5 molar. Okay, so that is the solubility of barium sulfate. How can we say that? Now, because the ratio between the barium over here and then barium sulfate is 1 to 1. So we can simply say that, okay, the solubility of barium sulfate is 1.0 times 10 to negative 5. So if we want to find in grams per liter, you can just grab that 1.0 times 10 to the negative 5 mole of barium sulfate per 1 liter. Multiply that by its molar mass, 1 mole of barium sulfate. The molar mass is 233 grams. Multiply the two value, the answer come out to be 0.0024 grams per liter. And that answer this question. Let's move on to next one. What if you have something like this, magnesium fluoride? The difference between this problem and the barium sulfate problem is because it's this. Magnesium, for every 1 mole magnesium fluoride will give you 1 mole magnesium, and it will give you 2 fluoride ion. So the ratio of the ions is not going to be 1 to 1 anymore. This is 1 to 2. So if you want to write the expression, the KSP is going to be equal to the concentration of magnesium ion multiplied by the concentration of fluoride ion and square because of this value. Plug in the KSP value. You have 5.2 times 10 to the negative 11, which is equal to let's say that the concentration of magnesium is X, of fluoride is going to be 2X. So magnesium is X, the fluoride is 2X, right? And then you have to square it still. So you have 5.2 times 10 to the negative 11. And then 2 square is 4. X squared times X is X cubed. So you want to solve for X, which will represent the concentration of magnesium ion. It is going to be root 3, okay? And then 5.2 times 10 to the negative 11, and then divide by 4. And then this X, which represent the concentration magnesium, will come out to be 1.4 times 10 to the negative 4 mole per liter. Okay, then we can say that the solubility of magnesium fluoride is equal to 1.4 times 10 to negative 4 because the ratio between magnesium and magnesium fluoride is 1 to 1. If you want to find in grams per liter, it is 1.4 times 10 to negative 4 moles per liter, mole of magnesium fluoride, okay, per 1 liter. Multiply that by the molar mass. 1 mole of magnesium fluoride, and the molar mass is 62.3 grams, okay, and then multiply the value, you have 0.015 grams per liter, and that answered the second question. So the third one here, I just want to point out to you that you have to be really careful when you compare the KSP value. Now for example, okay, so if you have the silver chloride over here, okay. So you have silver chloride over here, okay, and you can see the ratio of the cation and anion, it is 1 to 1, right? 1, 1. Okay, the KSP is this value. So now, if you want to compare the KSP value, whether the solubility is high or lower, you have to look for the salt that has the same cation and anion ratio. For example, you have silver bromide, and let's pretend that um, it has the KSP value. Ah, that is equal to 1.0 times 10 to negative 12. This is a pretend value. You can see that this value is larger than this value, so you can simply say, oh yeah, the solubility of silver chloride is larger than silver bromide because this KSP is larger. But if you want to compare with something, the compound or the salt that has the cation and anion ratio that's different from this one, you see this 1 to 1, right? This is not 1 to 1 anymore, it's 2 to 1. And you look at the KSP value, this one is smaller than the KSP of silver chloride. So if you don't think about it, you just can assume you can look at it and you can say, oh my god, this solubility of this must be greater than that. No, you can't do that. Okay, you have to actually calculate the solubility of the salt when the cation and anion ratio are different, like this case and this case. Let's find the solubility of silver chloride. Okay, so x would be equal to square root 1.8 times 10 to negative 10. If you wonder how I come up with this, go back, look at the two problem before this one. Okay, so you know why I put x equal to square root of ksp now, because this is equal to x is equal to x, right? And then solve for that. It is going to come out to 1.3 times 10 to the negative 5. That is the solubility of silver chloride. Now, for this one, okay, this is going to be 2x and this is x. Okay, so the x value is going to be equal to root 3 of the 9.0 times 10 to the negative 12. This is your KSP, and divide by 4, right? Look at the problem before this one. So the x will come out to be 1.4 times 10 to the negative 4, okay, molar. Now, compare. Okay, let's bring the highlighter. Oh, you can see here the solubility of ferrochromate is larger than this one. Although the KSP is smaller, but the solubility is larger, so you cannot compare the KSP of the salt that has different cation and anion ratio. Okay, that's it.